Acids and bases. This tutorial shows how you can use Kb to find K equilibrium. This is very similar to using Ka to find K equilibrium. Note the differences of Ka, Kb, and K equilibrium. K equilibrium is a competition between two acids if Ka values are given, or two bases if the Kb values are given. Here is an example of Bronsted-Lowry acid-base reaction. This is a reaction where only the Kb values of the bases are known. Methylamine reacts with hydrofluoric acid to produce the conjugate pairs, the fluoride ion and the methyl ammonium ion. The equilibrium expression for this reaction is given below. The concentration of the product ions multiplied by each other divided by the concentration of the reactants. The numerical value of K equilibrium can be determined by the value of Kb of the bases. There is no need to change these values to Ka. The next slide will show the rearrangement of the equations. Acids and bases. Kb is the base ionization constant. For a general base represented by B, it reacts in the presence of water to produce the ions BH plus and OH minus. The equilibrium expression for Kb is given below, where Kb is equal to the concentration of the product ions multiplied by each other divided by the concentration of the base. Water is a liquid, its concentration does not change, and the value of it is equal to 1. Note, for Kb, these are ionization reactions in water. A hydroxide ion is always on the product side. This slide shows how you could quantitatively determine the numerical value of K equilibrium from Kb. First, write the base ionization in water for each base. Then, write their Kb equilibrium expression. Isolate Kb and the hydroxide ion concentration on one side of the equation and the base and its conjugate acid on the other side. Note that for the fluoride ion, this must be inverted so that the hydroxide ion concentration is the numerator and Kb2 is the denominator. Then write the K equilibrium expression and substitute the Kb and hydroxide ion concentration for the base and its conjugate acid concentration. By canceling the hydroxide ion concentration, the final mathematical equation is a ratio of Kb1 to Kb2.